Okay, so now we have our base geometry sorted. So that's our electron group geometry. We need to talk about molecular geometry, which is not always the same as our electron group geometry. So when we're going full on to naming the shapes of molecules, we need to be able to say the shapes where we see that the lone pair is influencing that molecular shape, but then we say what we see without the lone pair. Okay, so if our steric number is 2, our only option is linear. Even if it is just like a 2-atom molecule and one of those was a lone pair, the shape would still be linear, okay? But when we start getting to fun stuff, like if I could have my mouse back, that'd be great, thank you. If our steric number is 3, so if all of those groups around the central atom are just atoms, our molecular geometry will be trigonal planar. But if one of those groups is a lone pair, what do we see that is not the lone pair? That shape is what we call bent or angular. And the ideal bond angle for that would be 120 degrees. For our steric number of 4, if all those 4 atom groups are atoms, sorry, the electron groups are atoms, then our molecular geometry is tetrahedral. But if one of those is a lone pair of electrons, the shape that we see is a triangular-based pyramid shape, okay? So that's why it's called trigonal pyramidal. If 2 of those electron groups are lone pairs, so you have 2 bonded atoms and 2 lone pairs, that's a bent shape, but because it's derived from the tetrahedral electron group geometry, that ideal bond angle is 109.5 degrees, not 120 degrees. For the steric number of 5, if we've got all bonded atoms, no lone pairs in our central, that molecular geometry will be the same name as the electron group geometry, which is trigonal bipyramidal. If one of those electron groups is a lone pair of electrons, so we've got 4 bonded atoms, 1 lone pair of electrons, that would be called the seesaw shape or the sawhorse shape. Notice the lone pair of electrons goes on one of those equatorial sites. That is actually proven that it goes on that site because there's only 2 90-degree repulsions there between the electron clouds on the apical or axial atoms, okay? So there's less repulsion there than if it was on one of the axial sites, there would be 3 90-degree repulsions. Remember, electrons don't like other electrons, so they repel each other. So that is where that seesaw shape comes from. If you imagine rotating that 90 degrees anti-clockwise, it would look like a little seahorse kind of thing. You can make it go up and down. If you have 2 lone pairs and 3 bonded atoms, again, that second lone pair is going to go on an equatorial site. That is what's called T-shaped for reasons which I'm sure you can imagine if you rotate that particular drawing 90 degrees clockwise. If you have 2 bonded atoms and 3 lone pairs, which does happen, the bonded atoms will be on the axial site. So that is essentially a linear molecule with all the 3 lone pairs taking up those equatorial spots. Then finally, octahedral is all we need to worry about. So if all 6 of your electron groups are atoms, well, then your molecular geometry is octahedral. If one of them's a lone pair, then that is a square-based pyramid shape, right? If you take any one of those apical sites and make it a lone pair. So we call that square pyramidal. If you've got 2 lone pairs and 4 bonded atoms, the lone pairs will arrange themselves so they are opposite each other, which leaves you with a square planar shape. If you keep going, you end up with a T shape. And then if you finally take off another bonded atom, so you've only got 2 bonded atoms, well, that is going to be linear. Okay, so hopefully that helps you guys out a little bit. So I've summarized the names there just to help you out a little bit. So with all these kind of questions, you have to draw the Lewis structure of the molecule first. So we got nitrogen, 5 valence electrons. Yes, we're still doing this every time. I know, right? I know, you got to do it. And then we got 6 valence electrons from the oxygen and 7 from the chlorine. So we have a total of 18 valence electrons, okay? So what is going to be our central atom? I would assume that it is nitrogen unless told otherwise, because nitrogen would have the highest bonding capacity, wants to form the most bonds. So I would usually put that in the middle. So our method would normally be to make nitrogen the central atom, and then I'm going to join it up with an oxygen and a chlorine. Join them up with single bonds, and then go ahead and complete the octets on the atoms around the outside. And remember, that is just going to be our first approximation of the structure. And then we're going to work on making sure we got the right number of valence electrons and making sure nitrogen has an octet and yada, 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 yada. All right, so come here, that is a lone pair of electrons. Okay, so we should have Sorry for the vastly different sizes of electrons, but you know, I'm using a trackpad mouse. All right, so right now we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, which is not enough, right? So when you're at this stage, you've got 16 valence electrons, it's not enough. What we need to do is add a lone pair to the central atom, and we got room to do that, right? So now we've got our 18 valence electrons. Okay, so then if we look around the nitrogen, it's not happy. It's only got 2, 4, 6 electrons around it. So the one way that we can definitely complete the octet is to take a pair of lone pair electrons and move them so that they are shared. That is not the thing I wanted to touch. Hang on. So that they are shared between the oxygen and the nitrogen in this case, rather than just belonging to the oxygen. Okay. Why did I take them from the oxygen? Because A, halides don't really like to form double bonds. B, yeah, oxygen's more electronegative. It makes more sense that it's gonna do that. Okay, so if you're ever not sure, go with formal charge. Okay, but you do not want to be making double bonds with anything in group 17 unless it's a dire emergency. So I am gonna just like undo that little thing I did there, and I'm gonna whoopsie, come back. I don't want to get rid of you. No. Come back, get rid of that lone electron. I did it, and then convert that into a bond. So now, if I look at that, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Nitrogen should have an octet, 2, 4, 6, 8. I'm happy with that. So that's what you got to do before you even get to deciding what the electron group geometry and therefore the molecular structure is going to be. So to get the steric number, I'm only counting the things around that central nitrogen atom. So there are 2 atoms bonded to it, the oxygen and the chlorine. It doesn't matter that the nitrogen-oxygen bond is a double bond, right? It's still like the things I've got to fit around the nitrogen. And there is 1 lone pair of electrons on the nitrogen. So that steric number is 3. So that means our electron group geometry is going to be trigonal, if I can spell it, planar, okay? So if you're not sure where that's coming from, I've got to have 1, 2, 3 groups of electrons around that central nitrogen. Okay, so one of those things is a lone pair. If I was going to like redraw this structure, I would draw it with my bonds kind of like a 120-degree angle like this. Okay, I'm just going to leave the lone pairs off a second. So my oxygen would be here, my nitrogen would be here. Come here, nitrogen. And my chlorine would be here, because that lone pair of nitrogen, electrons on the nitrogen is kind of taking up space in this area here. So that is about 120-degree bond angle, because it's based on the trigonal planar shape, although the amount of space that a lone pair takes up is not equivalent to the amount of space a bond takes up. This is a bit more advanced, but think about it, that lone pair of electrons doesn't have a nucleus on the other side forming a bond to attenuate that negative charge, so it's going to spread out a bit more and take up more space than if it was attached to an atom in a bond. So my molecular geometry then would be a trigonal planar electron group geometry with one of those sites taken up by a lone pair, so we would call that bent 120 degrees. Okay,